Here we have Philipp Mao. He's a PhD student at the University of Engineering of Lausanne. He is part of a Hexhive research team with Matthias Peyer, and he has an experience as a pen tester. What Philipp will present today is exploiting Android's hardened memory allocator. So what if a component that is meant to protect your heap is exploited to target Android system server? So Philipp will explain what is possible in this space. So give a warm welcome to Philipp Mao. Thank you very much.
Okay, thank you. So my name is Philipp, and I'll be presenting some research we did at EPFL together with Elias, Marcel, and Matthias. Maybe quickly about me. So my name is Philipp. I'm a PhD student, and I mostly focus on the security of the Android user space. I play CTF, and my favorite category is memory corruption. So if you're interested in any of those topics, please hit me up. But this talk's not about me. This talk is about Scudo, the titular hardened memory allocator. So what is Scudo? Scudo is a user space memory allocator. So it implements the dynamic memory allocation and deallocation APIs that you know and love, so malloc or free. There's two reasons why I'm talking about Scudo today. One is that Scudo is a hardened memory allocator. So it is designed to make the exploitation of heap-based memory corruption vulnerabilities either very difficult or even prevent the exploitation of those. And the second thing why Scudo is actually relevant is that since Android 11, so since 2020, Scudo is actually the default user space memory allocator in Android. So if you download the Android open source project, you compile it, Scudo will be compiled into your standard library, and all user space programs by default will use Scudo. And so back in 2023, we had a bunch of crashes in native libraries and apps, and we were triaging these crashes. We realized that the allocator that was used was not the standard Linux one, it was actually Scudo. And at the time there was no research, or there were no resources about how Scudo actually works. And we went down this rabbit hole of trying to figure out how does it actually work? If this is a hardened allocator, are our memory corruption vulnerabilities even exploitable anymore? And then after we figured out how the allocator worked, we actually tried to understand, okay, can we maybe even exploit the allocator itself? And so this is what my talk is going to be about. I will walk you through basically from sort of setting the stage of why do we want to exploit the allocator to the internals of how Scudo works, all the way up to actually the exploitation techniques that we found and a real world-ish example. So first off, maybe to get us all on the same page, what do I mean, or what is it actually when I talk about exploiting heap allocators? There's three components involved there. There's the application. This is the code that's written by the developer, and this one uses malloc and free to allocate and deallocate memory. There's the allocator. This is a piece of code that implements those functions, and this one, the allocator manages heap memory. Heap memory is just the memory region where this dynamic memory is allocated and deallocated. And all these three boxes run in the same process. Now it all starts with the application being buggy. So there's bugs, and these bugs expose heap memory corruption vulnerabilities that are attacker, or that may be attacker triggerable. Now when the attacker triggers these heap memory corruption vulnerabilities, the attacker can corrupt memory on the heap. There's two types of data that the attacker can corrupt. One is application-specific data, so that is data that is stored there by the application itself. The other is inline heap metadata. Inline heap metadata is data that's stored on the heap, but it's actually stored there by the allocator itself, not by the application. And this inline heap metadata is just a way to basically, for the allocator to kind of keep track of the allocated memory blocks. And of course, when the attacker corrupts this inline heap metadata, when the allocator interacts with the inline heap metadata, there's a potential to basically mess with the allocator. And for the standard libc allocator, there's a whole dictionary of techniques for different versions and different corruption primitives on how to get either arbitrary write or code execution. And in our research, we asked the question, okay, Is this actually possible to do for Scudo? Because Scudo is supposedly hardened against corrupting the heap state. Now, why do we want to do this? Obviously, because it's fun, but also because if you have a memory corruption vulnerability in a program that uses Scudo as an allocator, in order to sort of assess the exploitability and figure out if this is like an interesting bug or not, you kind of need to have the whole toolbox available to you. And one piece of the toolbox on how to exploit a heap memory corruption vulnerability is exploiting the allocator itself, as opposed to application-specific data. You might be wondering, okay, but we're on Android, isn't this all Java? Well, actually, no. A huge part of the code that is running inside of the Android user space, even in apps which are very Java heavy, is actually C++ code. And C++ code is very susceptible to such heap-based memory corruption vulnerabilities. All right, so in order to actually exploit the allocator, we need to understand how the allocator works internally. So in this section, I'll walk you through these 5 points. Basically, we'll talk about what inline heap metadata is stored by Scudo on the heap, how Scudo protects that inline heap metadata, and then the 2 types of chunks Scudo actually tracks. So first off is what inline heap metadata is stored on the heap by Scudo. And it's actually just one piece of metadata, which is the chunk header. So here we have the memory just around an allocated Scudo chunks. These 5 nines, these are some ASCII characters that have been stored there by the application itself. This pointer here is the pointer that is returned by malloc, so this points into the chunk body where the application stores the data. And just behind the chunk body, so at lower addresses, there's 8 bytes of chunk header. And then just at higher addresses, there's the chunk body where the application actually stores the data itself. And this chunk header is the only piece of metadata that Scudo actually stores inline on the heap. What's inside of this chunk header? There's essentially 3 fields. The first one is a class ID. This is just categorizes the chunk or just places the chunk into a size bucket. So there's class IDs 1 to 32 for size 0 to 64K. So a chunk of 64K bytes would be class ID 32, a chunk of 1 or 0 bytes would be class ID 1, etc. There's the state. The state essentially tracks if the chunk is currently allocated, so it's used by the application, or if it's freed. And then there's the requested size. So this was just the parameter that was given by the application to the malloc function call. But then there's also these 2 bytes at the end of the header. And this is where it gets a bit more interesting. This is the checksum. Basically, what Scudo does is it calculates a checksum using the address of the chunk, so the address that was returned by malloc, a Scudo internal secret, as well as the data of the chunk. It does a bunch of CRC32 checksums, and it stores the resulting 2 bytes into the header itself. And you can think of this as a signature, because what Scudo does is every time it needs to parse a chunk header, so effectively when a chunk is freed, Scudo needs to parse the chunk header, Scudo will first recalculate this checksum. So here we have the original chunk header, everything is fine, the checksum matches, and Scudo will basically actually parse the data inside the header. Let's say we have an overflow, and this overflow actually overflows into the chunk header. So here we have an overflow coming from lower addresses, and it clobbers the data fields inside of the chunk header. Now when Scudo frees this chunk, Scudo recalculates the checksum, but of course the checksum is not going to match the checksum that is stored inside of the chunk header, and Scudo will just basically abort the process will crash, and basically before attacker controlled data, before this clobbered data here is parsed. And this, of course, is a huge problem if you want to actually exploit the allocator, because we're interested in corrupting inline heap metadata, but if there's a checksum, it's very painful to actually corrupt this data. Next up, there's 2 types of chunks that Scudo tracks. There's primary chunks. These are chunks in class ID 1 to 32, so chunks sizes 0 to 64K. These chunks are basically stored in the main heap region, and this is, you can see on the right, and each of these read-writable sections is basically assigned a class ID. So for example, 2 allocations of size 0x18 are stored in the same memory, are assigned class ID 2 and are stored in the same memory region. And then an allocation of size 0xA8 is stored, has class ID 6 and is stored in another memory region. This is a kind of a lightweight way of trying to separate different types of objects. And also there's guard pages in between these regions. So these are basically pages that are mapped without any permissions. And when you have an overflow and you hit these guard pages, your process will segfault. So you basically isolate different class IDs between each other. And inside these class ID memory regions, there's another security measure, which is randomization. So Scudo will actually randomize the heap layout for every time a program is run, which effectively prevents attackers from being able to predict the heap layout. So here we have a program that allocates 4 chunks. And in the first run, the heap layout kind of looks like this. You run the program again, and the heap layout is different. And this makes it very hard for an attacker to kind of build a heap layout that will, or to predict the heap layout, which is a very important in heap exploitation, because usually you need to have a specific heap layout to actually exploit a heap vulnerability. Now, there's also what's called secondary chunks. Secondary chunks are chunks of sizes bigger than 64K bytes. And these secondary chunks are allocated using the system allocator. So they're just memory mapped as their own memory region. So here we have an allocation of size 0x20,000. And this chunk is just mapped inside of the memory, inside of the address space in its own region. Now chunks of our secondary chunks are assigned class ID 0. So they'll have a normal chunk header, but the class ID will just be 0. What's very interesting about secondary chunks is there's actually additional metadata Scudo stores inline to kind of keep track of secondary chunks. This is the secondary chunk header. So here we have the memory around the allocated secondary chunk. This here is the standard Scudo chunk header. At higher addresses, this is the chunk body. And if you look at this chunk header, the class ID is 0 because it's a secondary chunk. And then just below, or sort of at lower addresses than the standard chunk header, is the secondary chunk header, which is additional metadata that's used to track secondary chunks. And so inside of this secondary chunk header, you have a bunch of very interesting fields. You have a previous and a next pointer to a doubly linked list of allocated secondary chunks. You have the map base fields, which basically point to the base address of the memory mapping with and without guard pages, and also the sizes. And if you look at this secondary chunk header, you might be saying, okay, wait a second, there's no checksum here and there's pointers stored here. So this is a very, very juicy target if we actually want to mess with the allocator. The problem is the secondary chunk header is in a very inaccessible location. So this is kind of the memory layout around a secondary chunk. You have a guard page, so no permissions there. The secondary chunk header, then the Scudo chunk, which is the standard chunk header plus chunk body. And then following that, you have another guard page. And you can see that writing to the secondary chunk header is very hard. You basically need almost an arbitrary write primitive in order to write there. And if you almost have an arbitrary write primitive, you don't need to exploit Scudo. You can just get code execution that way. So in conclusion, so this brings us to the end of the Scudo internals section. In conclusion, we only have one piece of inline heap metadata that is easily corruptible, which is the standard chunk header. But this standard chunk header is protected by a checksum, and it also doesn't store very interesting data. So what do we do? Let's take a step back and actually look at the Android user space to get some inspiration of how we might actually exploit Scudo. Now, the Android user space has a very interesting phenomenon, and that is that a lot of processes are actually clones of the same process. So here we have a bunch of processes running in the Android user space, and we have 2 apps running, and both of these apps are actually children or clones of the so-called zygote process. They've been cloned using the fork system call. The fork system call essentially just is a lightweight way to make a copy of a running process, and then basically there's a return code, and you can basically, checking that return code, you know if you're in the process that called fork or if you're in the child process, and then you can directly execute child-specific code. So both of these, the victim app and the evil app, were forked from the zygote process. Why is this done this way? Basically, it's a performance hack because fork is very fast. So if you start an app, it'll be forked from zygote and it'll almost start up instantly. Additionally, all the children or the parent and the child, when you fork, share the underlying memory until they're written to. And this drastically reduces memory pressure on the system because especially apps load like gigabytes of framework, libraries, and resources in their address space. And by sharing all of this read-only or read-execute-only memory, you reduce the memory pressure on the system to make sure that your Android runs smoothly even on low-end hardware. The problem with this approach, it's great for performance, very bad for security, because what happens when you fork, you create a copy of the process, which includes the ASLR layout. So essentially, all the children that are forked from the Zygote process share the same ASLR layout. Okay, that's already very bad, but additionally, you also copy the contents of the memory. And this includes the Scudo allocator metadata, which includes the seed that's used to randomize the chunk, the chunk layout, as well as the secret that's used to create the checksum of the standard chunk header. So all the children of the Zygote process share basically the same initial Scudo allocator state. And this has like huge implications for an attack scenario where one Zygote fork process attacks another Zygote fork process, because you have shared ASLR and a shared randomized secret, which means that the attacker can basically predict the exact addresses of chunks allocated in the victim. Additionally, because you have the secrets shared that's used to calculate the checksum, the attacker can also forge valid checksums. And given the two conditions above, exploiting Scudo now becomes much more feasible. So to conclude, maybe you might be wondering, okay, is this Zygote fork to Zygote fork attacker model even relevant? I would say yes. So in this attacker scenario, the attacker is a malicious app, which is a very common threat model for Android. And the victim is either another app. Of course, for another app, you need to have an IPC endpoint exposed by that app, and that IPC endpoint needs to call into native code. So it's a bit more of a stretch. But there's also system services that are forked from the Zygote process. And these system services are highly privileged user space processes that are basically used by apps to talk to the hardware. And these are usually implemented in C++, so there's a very high chance there's actually a memory corruption vulnerability there. And so just to conclude, basically on the main production deployment for Scudo, the security measures are voided by or in a very common attacker scenario, the security measures are basically nullified because of this forking that's done. And well, now we finally get to the exploitation part. So for the rest of the talk, we'll consider this attacker model, attacker scenario where a Zygote forked app is attacking another Zygote forked process. And I'll talk you through exploiting a heap buffer overflow to attack Scudo. So the first thing that happens is the attacker interacts with the victim in order to basically make it so the chunk from where the overflow happens is at a lower address than the victim chunk. This is possible because the attacker knows the exact addresses where the victim chunk will allocate, where the victim process will allocate its chunks. So this is our victim chunk, and the attacker triggers the overflow, and the overflow payload overrides the existing chunk header. And the attacker basically puts a chunk header into his overflow payload, where he puts a correctly signed or correctly checksummed chunk header. The attacker can correctly calculate the checksum because the attacker knows the address of the chunk, and the attacker knows the secret that's used to calculate the chunk header. So the attacker can forge a valid chunk header there, and the attacker places a chunk header with class ID 0 there. And when the victim chunk is freed, Scudo will first go in and parse the chunk header. So Scudo recalculates the checksum. The checksum calculation is successful because the attacker knows the address and the secret. So the checksum that the attacker put there is valid. Scudo continues and parses the data in the header. Scudo sees that the class ID of the chunk is 0. So Scudo will go just behind the chunk to parse the secondary chunk header. But this, of course, is disaster because the secondary chunk header here is part of the attacker's overflow payload. So the Scudo will think that like there's a bunch of, basically now the attacker has control over pointers that Scudo will parse. In this case, all the pointers are a bunch of A's, and Scudo will just segfault terribly. But of course, what if you put valid pointers in there? Right? This is where our exploitation techniques come in. But first off, so the main idea of exploiting Scudo is to sort of create a fake secondary chunk where the secondary chunk header of that fake secondary chunk is under the attacker's control. There's two ways you can do that. You can either overwrite the header of an existing chunk, the way we just did before with an overflow, or you can use an arbitrary free, so you can pass pointers, so the attacker can pass pointers of his choice to free and point that to attacker-controlled memory, where the attacker basically just forges a fake secondary chunk. And then when Scudo frees that fake secondary chunk, Scudo will parse attacker-controlled pointers in the secondary chunk header of that fake secondary chunk. And we basically found two techniques to basically mess with the fields inside of our fake, of the secondary chunk header of our fake secondary chunk in order to get an arbitrary write primitive. This is the forged commit base and safe unlinking technique, and I'll walk you through both of them. First off, the forged commit base technique. It's very simple actually. So you forge your fake secondary chunk. So here we have so we'll again use an overflow to override an existing victim chunk. So here you have your existing victim chunk. It has class ID 2. The attacker triggers the overflow, and the attacker overflows into the existing chunk headers and places a chunk header with class ID 0 there. And the attacker places a fake secondary chunk header behind, where the attacker just places his target address, where the attacker wants to get an arbitrary write. So the attacker wants to write to a particular address. In this case, it's this 7F46 whatever address inside of the libc writable section. The attacker just places that address with an offset into the fake secondary chunk header. And then when this fake secondary chunk is freed, what Scudo will do is Scudo will just take that address and put it into the secondary chunk free list. So this chunk is freed, and if you look at the memory inside of the secondary chunk free list, the attacker-controlled address is inside of the free list. Maybe just a bit of background. The secondary chunk free list is a list of pointers that points to free secondary chunks. And basically when a secondary chunk is requested, Scudo will first traverse the free list to check if there's an adequate chunk that might be used to sort of handle this allocation from the secondary chunk free list. But of course, when you place arbitrary pointers in there, you might be able to also, you can get Scudo to return arbitrary pointers from the free list, which is exactly the third step of our technique. Basically, the attacker requests a secondary chunk to be allocated, and that secondary chunk will be served from the secondary chunk free list and will be allocated at the attacker's chosen address. And now the attacker has achieved his arbitrary write because now the attacker has basically placed a chunk at his chosen address. So this is what happened here. You can see there's a chunk allocated at the address that was basically put into the fake secondary chunk header before it was freed. And Scudo actually wrote the secondary chunk header there with class ID 0 and a semi-valid secondary chunk header. So this is the first technique. Basically, you poison the secondary chunk free list by placing your target address into the map-based fields of your fake secondary chunk header. One requirement for this is that the attacker afterwards, in order to request this chunk, has to be able to allocate a secondary chunk. So the previous technique was pretty straightforward. The second technique is much less so. The second technique abuses the doubly list unlinking that happens when a secondary chunk is freed. So I was talking about before, when a secondary chunk is freed, or a secondary chunk header is part of a doubly linked list of allocated secondary chunks. And when a secondary chunk is freed, this chunk header, the secondary chunk header, is unlinked from the doubly linked list of allocated chunks. And unlinking from a doubly linked list is known to be potentially a way to exploit an allocator. The problem with Scudo is Scudo actually checks the integrity of the linked list. So Scudo will follow the next pointer and then follow the previous pointer and make sure that this points back to the start. Same for the other way around. So how are we going to exploit this unlinking? What we're going to do is we're going to craft a fake linked list between the fake secondary chunk header and a per class free list. What's a per class free list? A per class free list is just a free list for primary chunks of a specific class ID. So it's essentially just an array of pointers that point to freed chunks of a specific class ID of primary chunks. So for example, to a bunch of class ID 2 chunks that were freed before. And we'll basically forge our fake linked list because between this array in a per class free list and our fake secondary chunk header. The way this is going to look initially before unlinking is like this. You have your per class free list, and the first 2 entries in this per class free list point to our fake secondary chunk header, and then our fake secondary chunk header, the previous and next pointers, point inside of the per class free list. And when our fake secondary chunk is freed, the fake secondary chunk is unlinked, and the per class address itself, will be written into the per class free list itself, which is obviously very nice for the attacker because when the attacker allocates from that per class free list, the attacker actually gets a chunk overlapping the free list and can thus control the address of future allocations. Now you might be asking, okay, all cool, how do we actually craft this fake linked list, right? The way we're going to do this, we need very powerful primitives. We need an arbitrary free. What we're going to do is we're going to basically free a fake primary chunk that is placed at the start of our fake secondary chunk twice into the same per class free list. So there we have 2 pointers at some consecutive indexes in the per class free list pointing back to our fake secondary chunk. So here we have our victim chunk. This will be changed to a fake secondary chunk. And at the beginning of where our fake secondary chunk header will be, we wrote a primary chunk header that will free twice, making sure to reset the state of this fake primary chunk so Scudo doesn't actually detect the double free. And when we did that and we inspect the memory in the per class free list, we'll have 2 addresses in the per class free list pointing to the start of our fake secondary chunk header. And then in order to complete our linked list, we'll basically we update our fake secondary chunk header to point into the per class free list. And now we know the address of the per class free list because this is also part of the memory that is copied on when forking. So by inspecting, so the attacker can basically inspect the address of his own per class free list, and from that knows the address of the per class free list of the victim process. And here's how the final linked list looks. You can see the 2 pointers, the previous and next pointers, in the fake secondary chunk point into the per class free list, and the per class free list points back to the start of the fake secondary chunk. And now when the victim chunk is freed, the unlinking takes place and the address to the per class free list itself is written into the per class free list. And now when the attacker allocates a primary chunk from that specific per class free list, the attacker Scudo will allocate a chunk inside of the per class free list that'll overlap the remaining array of free pointers, so the attacker effectively gets control over the per class free list and can control future allocations. Okay. So yeah, unfortunately this technique is coincidentally fixed in Android 14. So if you look at this array, this is an array of the per class free list, this is an array of compact pointers. Since Android 14, these are not raw pointers anymore, just offsets into the primary chunk's memory region. And of course, if it's offset, if it's just offsets, we cannot forge a fake linked list because we need raw pointers. I say coincidentally fixed because we did not disclose this, and the commit message inside of the Scudo source code doesn't imply any sort of security measure. So yeah. So in conclusion, this is the safe unlink technique. It's much more theoretical than the other technique. You need a lot of very strong primitives. You need an arbitrary free and a lot of control over the memory where you will forge your fake secondary chunk. And it's also coincidentally fixed since Android 14. But fortunately, Android 14 is still a very small market share. So if you're very lucky, you might be able to exploit this still. Okay, so now I was talking about all of this stuff, but it's all theoretical. Is this actually real? Is this actually true, what I'm talking about? So in order to show this, what we did is we basically forward ported an old CVE to Android 14 and basically exploited used one of our techniques to exploit the system server process from a victim app to get code execution there. We forward ported this very old CVE. The CVE has kind of a cool history because in 2015 it was actually used in a very similar attack scenario to attack the surface flinger process from a malicious app, and it actually exploited jemalloc, so the previous heap allocator. And basically, 10 years later, we used the same bug to exploit Scudo, the supposedly more hardened allocator, right? And we'll exploit the sensor service that's running inside of the system server. The system server is a highly privileged process that hosts a bunch of system services, and the system server is also forked from Zygote, so it's part of our attacker scenario. First off, let's understand how this CVE works. So it's a vulnerability in this parcel read native handle function. A parcel is essentially a byte string that is sent by a app when doing IPC. So this is binder IPC, the main way or the main IPC mechanism in Android. The caller just sends a string of bytes, and then the server essentially deserializes objects from this string of bytes. And what happens here is a native handle object is deserialized from the input byte string, which is an object that holds a bunch of integers and a bunch of file descriptors. And the bug is here. Basically, at the beginning, this function reads out two signed integers, the number of file descriptors and the number of ints. And the problem is these numbers may be negative. And further down, this will lead to a heap buffer underflow. This read function reads out a bunch of size bytes from the attacker-controlled byte strings and writes it to the first argument, which is a pointer. And in this function, this pointer points to h, the data member of the h variable, which is just a chunk that was allocated on the heap, plus numfds, which if numfds is negative, this can point behind or to a lower address than the allocated chunk. So this can lead to a heap buffer underflow. And of course, a heap buffer underflow is super convenient for us to exploit Scudo because we can basically override the allocated chunk's header basically change the allocated chunk from class ID, whatever it is allocated, to 0, and place our fake secondary chunk header there. The code path inside of the sensor service to trigger this bug looks like this. Basically, when we call the create sensor direct connection command, the system server goes down this code path. It calls data.readNativeHandle, where data is just our input byte string, and this will trigger the heap underflow. So it'll allocate a chunk on the heap and then trigger the underflow. Further down, there's some application-specific code. We're just going to exit early there because we passed some invalid values. And then later on, the allocated chunk is freed. So this is essentially the ideal code path when we want to exploit Scudo. We're going to trigger we're going to allocate a primary chunk. We're going to trigger the overflow and basically replace the allocated chunk with a fake secondary chunk. And then that fake secondary chunk will be freed, which if we do the forced commit based technique, will place a stack address to the main thread of the system server into the secondary chunk free list. This is the first IPC request we send. Basically, you can see there's the create sensor direct connection command. We send -23 file descriptors. This is going to make it so when in parcel.readNative, when the read function is called, this will point to exactly the start of the fake secondary chunk header. And then we also, inside of the body, we've sent the fake secondary chunk header, which contains a map base that points to a stack address of the system server. And the fake secondary chunk header that we use to override the existing chunk header will have class ID 0. And again, this is all possible. We know the stack address of the main thread because, again, the system server is Zygote forked, our attacker app is Zygote forked, and the address of the stack is also the same. So when this IPC is processed by the system server, it triggers the underflow, it'll free our fake secondary chunk, and it places a stack address to the main system server thread into the secondary chunk free list. And then we'll send a second IPC request that allocates that secondary chunk and essentially lets us allocate a chunk on the stack, and we'll hijack code execution by writing a rob chain at an offset into this chunk. And basically this rob chain just calls logcat with our string And well, when this works, if you want, I have this as a demo later on. You can just approach me. And when this works, it'll print this string to the logcat and just crash. There's some complications. I think the main one is that when you actually want to exploit the system server, predicting chunk addresses becomes much harder because there's about 180 threads inside of the system server. So you don't actually have the sequence of allocations and deallocations is not deterministic because there might be some racing between the threads. And so the way we address this is like twofolds. One, if you incorrectly guess the chunk address, so the address where read native handle allocates its chunk, if you incorrectly guess that address, your checksum is going to be wrong, and Scudo will abort the process. When Scudo aborts the process, the system server crashes, but it'll be restarted by the Android init process. So if you fail, you get another attempt. And actually, if you fail and the system server reboots and you try again right away, the heap state is in a much more predictable state. And then we allocate the read native handle chunk in class ID 32, which is the biggest class ID of primary chunks. And we found that this was the least used, so it was easiest to guess the chunk address there. And both these things result that after crashing the system server once, our exploit will work in around 10-ish attempts. There's some more complications, but I'm going to skip over this because I'm a bit short on time. But if you're interested, just approach me. Basically, this is our case study. We sort of forward port an old CVE to show that we can actually exploit Scudo in a real program with a real bug using one of our techniques. Yeah. This is the end of the talk. Basically, there's a few things of Scudo I didn't cover. Scudo has a quarantine mechanism, which is a delayed free list to make exploiting use after freeze harder. There's some other research that actually covers this much more, but I glossed over this because it's actually not used on Android, and because it has a huge performance impact, I don't think it ever will. And then there's also MTE, memory tagging extensions. Scudo has very nice support for that, and if you have a Pixel phone, if you activate this experimental feature, you'll actually have Scudo running with MTE, and this will make our exploitation techniques almost impossible because you basically would need to forge your fake secondary chunk at a specific area where you have like very specific tags, which is almost impossible. And yeah, that's the end of the talk. If you're interested in this or you have a bug in a program that uses Scudo, we have a GitHub repository with where you can find a GDB plugin to basically analyze Scudo heap state. There's also exploitation templates to basically exploit a heap menu using using both our techniques. And then we also have all the code for the proof of concept that I showed you before to run this or reproduce it. Thank you for your attention.